No.
All
right. So let's see. Where are we at? There we are. We're going to start talking about collisions. Now, there's elastic collisions and then perfectly inelastic collisions. All right. So this can go in the big blank space where you have a big blank space. Okay. On your notes. All right. So elastic collisions, they bounce. Okay. Elastic. That kind of makes sense, right? It bounces, and momentum is conserved. Okay. So the initial momentum is equal to the final momentum. Now, the biggest difference between elastic collisions and perfectly inelastic is that the inelastic stick together. Okay? If the inelastic stick together, is our kinetic energy conserved? Our kinetic energy? Our mechanical would be conserved.
Ask the question again.
If, so you see this example down here where the ball hits the big ball and it sticks to it. Would the kinetic energy, so would there be energy lost?
I don't think you can lose very well.
You can lose it to other things.
I don't think it would be lost. I think it would just go backwards. So then it would be like going from positive to negative. Because it would just bounce back. Right?
Maybe so.
It makes my head.
We just started talking about
I
it.
know.
Question,
So
Cole,
you're
I got a question for you real quick.
Oh,
What did you win 10-1 at?
what?
You walked into class.
Oh, we won at soccer, yeah.
Ah.
We got up 7-0.
Was it really like the Kingdom team?
It was a Kingdom team. But one of our players, they were playing really dirty, and one of our players got slammed into a wall and had to get stitches all down.
What team? Wow.
Just Kingdom.
Brazil versus
Did
Germany.
they like sign up on a sheet?
Beneath had to get like stitches.
He told me he ran into a door.
He did not run into a door. A
He
girl
told me he ran
slammed
into
him
a
up
door.
against the
All
wall.
right.
Yeah.
We good?
Yeah, okay, anyway, back to my question.
Back
for
to
you.
the question.
Okay, so is inelastic collision similar to like when you throw like a wet piece of clay at his door?
I mean, there are
No.
There's three.
Because,
Well.
no, because you're going to have a velocity here. So the
Oh, so that
the
has
other
to be
object is
moving
going to be
too.
moving. Okay. So let's check out this box. Now, do you have to copy this entire box? It's up to you. Okay. Now, if we look at this, inelastic. So a general inelastic collision. Objects will bounce off of each other. Momentum is conserved. As you guys can see, that's our goal. Yeah, that's our goal. All right. Now, in a general inelastic, is kinetic energy conserved? No, kinetic energy is converted to other forms.
Can all of it be converted or not just half of it?
Can all of it be converted? The only way you can't get rid of all the energy.
So what does it mean by momentum conserved?
So mass is going to be the same.
Nothing. I don't know if
So, well,
like stuff is good.
your P final is going to equal your P initial. All right, so the mass final. So the mass times velocity final is equal to the mass times initial velocity. So basically, the previous example, you had a big object and like a small object. So the mass is different for those two objects, but when you look at for
it to be the same, the little one would have to be going way faster than the big one.
No, my
Right.
Okay. All right.
okay, so if you look at a perfect, so this is the key difference. So you have a general inelastic, you have a perfect. They stick together. Okay, objects stick together. Momentum still conserved. Kinetic energy is converted to other forms. Now, when we got to elastic bounce off of each other. All right, that is where kinetic energy is conserved. Okay, that's where kinetic energy is conserved. And then explosion. Objects break apart. Yes. All right. We're not really going to focus on explosion too much, but we are going to focus on these.
Did you just whip out an iPad?
Yeah, I
Took a picture
Yeah.
of all the notes.
Yes.
Not a bad strategy.
Saves me time.
It worked.
I'll post the slides here after. Actually, I think I already posted the slides. Okay, so we are going to look at these different examples. All right, and to start off, we're going to look at perfectly inelastic. And we're going to start off with perfectly inelastic. So let's go back. Perfectly inelastic objects stick together. Momentum is conserved, but the kinetic energy is converted to other forms. So when we look at this, the objects sticking together. Here's an example. You guys see that down there? Sorry about that. We didn't do the riddle for today.
Is it your hand?
Oh yeah, we did. Yeah, we did.
I got it like the first 5 seconds.
Yeah.
Wait, isn't it your hand?
It is your it's your left hand.
Yeah.
It's interesting because when you put your hands together, what thumb's on top?
Your left or what?
Mine's my left because if you do right, it does not depend. You have a preference.
No, I mean, everybody, yeah, that's what I'm saying. Everybody has a
Oh,
preference, but it's not, nobody does both.
I was gonna say, what's it depend
No,
on?
it's-
So one way feels right.
I classify-
That is weird.
Left is always right.
My left is on top, but
No,
some
yeah.
people's right's on top. It just depends on how you do it.
Yeah.
No one else classified.
Wait, who here is right-handed? Okay, you're right-handed, then maybe the left-handed.
I'm left.
All right.
That's weird.
Yeah.
I'm gonna try to make a connection, Andrew. Why do you have to mess it up?
Yeah, well, gotta use scientific method.
Huh?
I'm suing you.
Scientific method.
Not letting you do it.
All right. So if we look at this example, example number 10.
Because you don't even adopt a 17-year-old kid, but
Here we go.
you can't
It is. An 1,875 kilogram car going 23 meters per second rear ends a 1,025 kilogram car going 17 meters per second on ice in the same direction. The two cars stick together.
You know.
So, if you look at this example, between what speeds do we know the vehicles will be going? How fast do we know the vehicles are going to be going? 17 to 23. Right? We know that. All right? They're perfectly inelastic. What speed? Let me zoom in a little bit. What will be going? We know they're just going to be going 17 to 23 meters per second. Okay? Now, B says, how fast do the two cars move together immediately after the collision? Okay, this is a little more complex. Okay, so we know we have our momentum initial, momentum final. Right? I'll zoom. Actually, I'll just make this large. There we go.
It kind of throws me off that momentum's P.
Yeah. It is weird, but like M is usually mass.
Well, can you do
Let's
capital
do it,
letters
yeah.
and lowercase fast?
No. uppercase M is,
Those are more.
Moles.
yeah.
Ugh.
Uppercase M is actually molarity. Moles is
Oh,
N.
well, I know it's one of those.
Stupid
small
molarity.
I don't remember seeing that.
It's a little tricky.
That's chemistry stuff, we don't need that.
Yeah, why would you need that?
All right. So if we look, we know.
I was close.
So let's say we know the mass of car 1 times the initial velocity of car 1. And we know the mass of car 2 times the initial velocity of car 2. Okay. So the mass of car 1 is 1875. The velocity of car 1 we said was 23. Plus the mass of car 2 is 1025 times the velocity is 17. So that is going to equal my momentum in the final. Okay? Now, my momentum in the final is my mass times my final velocity. And my question said, how fast are they going? So I'm solving for my final velocity, and they're together. So what's my mass going to be? Both of them, right? It's going to be 2,900. Does that make sense? And you just solve for the velocity. Okay. Anybody get an answer?
Like 21.
From 266, perfect.
Oh, you know what? I don't know.
21 meters per second. Okay.
Using significant
Are we gonna do a
figures,
slide
what is
when we
9
drive
plus
these cars
10?
on each other?
I don't see why not.
Can I be the front driver?
All right.
Says here, guys.
Just
That's-
tell him.
Yeah. Says five.
That's
That's
so stupid.
All right. So if you look at another example, a 1,200 kilogram car moving at 2.5 meters per second is struck head on in a collision by a 2,600 kilogram truck moving at 6.2 meters per second. The vehicles will stick together. What I want you guys to do, hopefully this is a clear choice. Which way are the vehicles going to be moving?
The direction of the truck.
All right, so it's going to be moving left. All right. So let's see. If the vehicles stick together, what is their speed immediately after colliding? Same thing we just did. Same thing we just did. So let's do it all. So what?
You subtract instead of adding,
So
since they're going in opposite directions.
Because, I mean, didn't we do that, like,
you're going to have mass times velocity. So the velocity of the van in this way is left. So it's going to be negative.
Okay.
So you're still
So you're still adding,
right.
but it technically would be subtracting.
Right.
Isn't it?
Yes. All right. So let's try that out. All right. So when plugging this in,
wait, would you subtract it?
I'm plugging this in. All right. Zoom out a little bit. All right. So you have mass of the vehicle 1, so 1,200. times its velocity plus mass of vehicle 2. No. Mass of vehicle 2 times its velocity
Wouldn't you subtract
negative 6.2.
like 1200 times 2.5? Wouldn't you subtract that since they're going opposite directions?
It's the same as what he has there.
You're adding it.
Something negative.
All right. So that is equal to the combined. Since they stick together, my combined mass is 3,800. What's my velocity final? Okay, what did you guys get?
Negative 3.5.
Negative 3.5. Perfect. All right. Everybody get that? So if we look, what is the kinetic energy of the cars after? Oh, what's my kinetic energy equation?
1/2 mass times velocity squared.
Ooh, ho.
So she does.
Came ready.
I did not have that.
Yeah, that's wow. Okay, you're the only one here.
Sometimes I just like, I don't know, it just comes out, yeah.
Okay. All right. So what is the kinetic energy? What did you guys get there?
23,000
Say it one more time.
23,000
23,000.
Joules.
Energy is in joules.
What would be the velocity? The negative 3.5?
So the velocity. Yep.
Would it be negative?
No,
I'm
it's
stupid. I'm
I'm
stupid.
prepared.
Doesn't matter. It's squared, but yeah. Theoretically, it would be negative 3.5. Okay. And then the last question, we'll finish on this one. Is the total kinetic energy less, more, or the same as before the collision? Would be less.
Let's go.
So where did energy go? Went into the other car. We probably lost a little energy to friction. We probably lost. All right. So that is perfect inelastic. All right. Tomorrow we're going to be driving some derby cars. Testing it out.
Let's go. For real?
Do you think I have derby cars in my back lot?
Well, I was
Yeah,
thinking like RC.
Oh, I don't have RCs, but
That would be kind of a cool or even hot tracks, like get two hot wheels tracks and then drive them at a certain distance and then the velocity would find.
that would be pretty impressive.
But you would need it to be straight diagonal, not curved, to turn all of us and right all of us.
What if you just fill out some guy
I am intrigued. I sincerely don't know how